right, we're back. We are back. Isn't that special? Welcome back to another exciting episode of Machine Shop Math. Now here we're going to take the circle and we're going to now apply trigonometry to the circle and work some things on a circle. You probably already figured out the bolt circle, right? A bolt circle. It's called a bolt circle because the bolts are arranged in a circle. Equal distance from the center. It better be equal distance from the center or it's not a circle, right? It would be like a bolt ellipse. Now in CNC land, your line of code for your can cycle, it wants to know the center coordinate of your bolt circle. And since we haven't located the center, we're going to assume, in this case, it's 0, 0. It's going to want to know the diameter of the circle, and it'll divide that by 2 to give you the bolt radius. And it's going to want to know the number of bolt holes, and it wants to know the starting angle of the first hole. So that's all programmed into the line of code. It's real simple. And then it does all of what we're going to do by hand. It does it in the background in the computer. But in order to check this stuff, and in order to do this by hand, we have to go back and use trig. Now we already know that we already know that sine controls the vertical and cosine controls the horizontal. We know that for a fact, yes? Okay. Now, let me get my pen. So, here we have 0 or 360. It's 0, and we go counterclockwise working the circle. You always go counterclockwise when you work the circle. Now, sometimes you've got to start someplace in the circle and go clockwise, go back this way to 0 to find the angle of the first hole. And we're going to do that. We will do that. All right. So remember that we start at 0 and we go counterclockwise all the way around the circle. Okay. Until we come back and close the circle at 360 degrees. All right. We always do that. Now, in this first example, we're going to assume the center is at 0, 0. 0 and 0. All right. So what is that? That's our x and our y. X is 0 and y is 0. Isn't that simple? All right. Okay, when we come back, we will, after this video, which should be video 10, part 4. Video 10, part 4. All right. So we've established our x and our y on here. So 0, 90, 180, and 270. All right. Okay. So let's go over here to our working sheet. Okay. Now here we have a bolt circle. Now, I didn't do 2 pages of this. All these angular values for these bolt holes were not on the original drawing. The only one that was given to you was 15. This one, it was at 15 degrees off at 270. So the first thing you're going to do when you look at a bolt circle, very first thing, remember, ignore these values right now. You don't know what they are. We locate the center of the circle. In this case, it's 0, 0. So that means all our calculations, even though we know they're relative, is that assuming the circle is at 0, 0. Now, if the circle was at 10 and 10, in other words, this bolt circle was in a part, we would have to add 10 to the x value and 10 to the y value for each thing we calculated, right? To get our true positioning in the world. So the first thing you do is you look at the drawing. How many bolt holes do we have? We have 6. 6 bolt holes. So 6-inch bolt circle. I mean, good God. We have a 6-inch bolt circle. 6-inch bolt circle. Yeah, you need to read this. 6-inch bolt circle. That means we need a bolt radius of 3 inches, right? Because if this is the circle, in other words, it's 6 inches all the way across here. 6 inches all the way across here. So we come up here and we read this. We have a 6-inch bolt circle. That means it's a 3-inch bolt radius. So it's 6 inches from this point to that point. It's 6 inches from this point to that point. That means that's the diameter of the circle. And we deal with the radius. So you divide 6 by 2 and you get 3. All right? You get 3. Now we have 9 equally spaced half-inch diameter holes. So we have 9. And they're equally spaced. So that means we have an angular difference, an angular variance. The angular difference between these two, is 40 degrees each. 40 degrees each. We take 360, divide by 9, because there's 9 holes, they're equally spaced around 360 degrees, and that gives you 40 degrees. Divide 9 into 360 and you'll get 40 degrees each. So that means from 135, from hole number 4 to hole number 3, assuming you can do a straight line, this is going to be 40 degrees. The angular difference between 4 and 3 is 40. The angular difference between 3 and 2 is 40 degrees. 40 degrees. And so forth and so on, all the way around the circle. So forth and so on, all the way around the circle. Now, let's remove this. Now, y'all are all smart enough to know that you can play this video back, right? Because it's recording. All right. So, but we don't know. We don't know in the beginning that 4 was at 135 degrees, or 95 degrees, or 55 degrees, or 15 degrees. We have got to start at 0 and go this way when we do our layout. But we don't know what they were located at. We weren't even given the value of 255 degrees here. All we were told on the drawing was that hole number 7 was located 15 degrees negative, in other words 15 degrees back towards 0 off of the 270 axis. Off of 270. This is 0, that's 90. That's 90, this is 180, and that's 270. And then 90 plus 270 equals 360. So we were told that hole number 7 is 15 degrees from 270. Now, so we're going to take 15 degrees because this is on the drawing. We're going to subtract it from 270 and you're going to get 255 degrees. So that's the angular value, the angular position on this circle of bolt hole number 7. Now going back in the negative direction, we know that each one of these going back in the negative direction, it was located 15 degrees, right? Hole number 7, 15 degrees from 270. So we subtract 15 from 270 and we get 255. Now we're going to have to go back and give an angular value for the position of these holes all the way back around to 0. And then we're going to start at 7 and go in the positive direction till we finish our holes. All right. So 40 degrees in the negative from 255 is 215. So that means number 6 has an angular position on the circle at 215 degrees. 40 degrees from 215 is 175. Right? 40 degrees from 175, 40 degrees 175 minus 40 degrees is 135 degrees. 135 minus 40 is 95. Right? You check my math with your calculator. 95 degrees minus 40 degrees is 55 degrees. 55 degrees minus 40 degrees is 15 degrees. So you might be given a drawing, even if you're doing a CNC program, and you're going to have to work it out. You might be given this drawing. You don't know what these numbers are. You do know that the drawing, the engineer says, or the designer says, we want this hole started at 15 degrees from this axis. So you would have to go through this exercise until you could find the starting angle of hole number 1. The starting angle of hole number 1. It's 15 degrees. 15 degrees. So in the line of code, you would say the center of my bolt hole is 0, 0, 0x, 0y. The diameter is 6 inches, and the angular, and there are 9 holes, and the first one starts at 15 degrees, and that's the value you would plug into the line of code to go into your CNC program, what's called a can cycle, for it to make this bolt circle. Now, if indeed this part was at x of 10 and y of 6, then you, instead of 0, 0, in the program line, you would put in 10 and 6. And it would do the very same thing you're going to have to do for the final and for this exam 3. But it does it much faster because it's in a little silicon chip doing its algorithm in the background. It's the same math. It's the absolute same math. All right. So what does all this mean? Well, you're going to take these angular values that you give for each one of these holes, and you're going to have to locate them someplace, because I don't know about you, but I can't remember all this. But we haven't finished yet. We're going to have to go in the positive direction. So we're going to take 255 plus 40. That gives us 295. 295 plus 40 degrees is 335 degrees. Okay, we've located them all. We've located everything. We've located everything. You need a chart, some kind of layout piece. Well, looky here. Oh my God, look what Mr. Wizard did for y'all. Okay. Hole number 1, 2, 3, 4, 5, 6, 7, 8, and 9. All right. If you miss any of this, go mop the floor at Walmart and drop this class, because you got hole 1 through 9. The angular values you just calculated. So you go up here to this chart, and you take each one of these values that you calculated for the location of each one of these holes, and you plug it in right here: 15, 55, 95, 135, 175, 215, 255, 295, and 335. And double check your work. You get any of this screwed up, you're going to get, the rest of this is wrong. The rest of it's absolutely wrong. Now, I even gave you the formula. Remember, x is controlled by the cosine times the bolt radius. And then we have a chart for the bolt radius. And how do we get the bolt radius? How do we get the bolt radius? We get the bolt radius from the bloody drawing. We said we had a 6-inch bolt circle. So half of the circle is 3 inches. Yes, that's your radius. Now, why do we care about that? I'll show you in a minute. And the rest of it is just absolutely plugging and playing. You take the cosine of 15 degrees, you multiply it times 3, and you get this number. You take the cosine of 55 degrees times 3, you get that number. You take the cosine of 95, you multiply that, and you'll get negative. Now, this is why we use absolute coordinate positioning on our bolt circles, because we don't have to remind ourselves that this coordinate is plus negative, plus plus, negative, negative, and plus negative. I said negative plus. Yeah, negative plus here. And we don't have to worry about that. We let our calculator determine what's negative. And here's where you will screw yourself so bad. You better put down the negative if it's a negative number. Now you know that all your x's in here should be negative, right? Because remember, we go back to the very basics. Over here in this coordinate, x is positive and y is positive. Over here, all your x's are negative and your y's are positive. Over here, both your x and your y are negative. Over here, your x is positive and your y is negative. So that gives you a good check if you're putting the right numbers down, the negatives and positives. All right? Okay. So let's do that. So you just run the calculator out. Cosine of 95 times 3, cosine of 135 times 3, cosine of 175 times 3. By now the FBI's got a pattern working, and they should be able to figure the case out, blah, blah, blah. And you'll get either your numbers are your x is positives or negatives, depending on what coordinate they're in. But your calculator will do that for you. It will give you a negative. Let's go over here, and if you don't believe me, let's take the cosine of 95 times 3. See what happens. 95. Go activate our trig, cosine. Oh God, it's a negative number. Wow, big surprise there. Times 3 equals a negative 261,467. Big surprise, right? And we're going to go to 4 decimal places in our angles here, so that's why that's rounded up to 5. Now we do the same thing for the sine. We take the sine of the angle. We're going to take the sine of 15, multiply it times 3, and you get that number. Sine of 55, multiply it times 3, get that number. Sine of 95 times 3, you get this number. Sine of 135 times 3, you get that number. Sine of 175 times 3, you get this number. Sine of 215, you get that number, which is a negative. Sine of 255 times 3, and you get this negative number. Sine of 295 times 3, you get that negative number. The sine of 335 times 3, and you get that negative number. Now, this is the x and y's for each one of the holes in the circle. Now remember, this is relative. This is relative because we have to assume that we start at 0, 0. Now, if, that's pretend time, for this conversation, the center of our circle was at an x of 10 and a y of 5. Then you take each one of these values in the x and you add 10 to it. So that would be 12.8, 12.8978. And if it was negative, it would be less than 10, right? That would be less than 10, less than 10, less than 10, less than 10. This would be greater than 10. This would be greater than 10. And you would do the same thing over here. So you would take your y position, where it actually is in the real world, at a y of 5, the center of the circle, and you would add that to this number here, and you would get 5.0. Oh, God. Now you see how easy it is just to screw up if you're not paying attention? You would get a 5.7765. And you do that for each one of these. You take the what I call the y-adder, or whatever, the absolute y value, the location of the center of the circle, and you would add it to each one of these numbers, and you would come up with a value over here, and the same with over here. So you're going to add 10 to all of these, and you're going to add 5 to all of these. Now some of you people are not paying attention. Now that means it's always 10. This could be, I don't know, this could be 5. And this could be 15. Who knows? Who knows? And then these values would change, right? These values would change. These values would change depending on, well, I just erased the 5. These values would change. They would change. So that would be 5 plus 2.89. That would be 7 point or whatever. This would be 15 plus that. All right, so it'd be 15. All right. Now, the advantage of doing it like this is, let's just say this bolt circle represents some kind of flange that your company normally puts out. Well, you always know the relative position of the holes on that bolt circle. And then let's say in one part it is at 10 and 5, and then the next part it's at 5 and 15. But it's the same bolt circle. Then all you got to do is just come to and add all of this. Most likely in a real production shop you're using a CNC machine. Okay, so that's your end result. That's your end result. Where is my bloody cursor? There it is. All right, that's your end result. Now, so why is the bolt radius so important? Well, I'm going to tell you. Okay. Remember our triangle I told you with trig and a right triangle? You can rebuild the world. Here's our right triangle for 15, where the vertical is going to hit the horizontal axis at 90 degrees. I guess we could use a different color for this bolt. Let's use a different color. Let's use green. I hope nobody's colorblind. There we go. So the values for these, this radius is still 3 inches. Yeah. And this radius here is 3 inches. And each one of these radiuses is 3 inches, right? Because it's on a circle. So, as you can see, 15 is going to have a larger x, and 2 will have a smaller x. If we bring 2 straight down, 90 degrees, it's got a smaller x, but it's got a greater y. And so forth and so on all the way around here. And then we'll let your calculator give you your negatives or your positives. Keep your negatives and positives straight. So we've now just taken the right triangle with trigonometry and thrown it in a bolt circle. And thrown it in a bolt circle to get our coordinate system. So how is that? That's pretty easy, I think. Isn't it? So there's your chart. Now you have a blank chart in your master formula sheet. If you want, I can put a blank one of these coordinate table templates in D2L so you can print out the blank one, or you can just go to the page in the master formula table. No, I've already given it to you. You can figure this out. Here it is right here. So this is page 22 of 22. So all you got to do is go up here and print just this one page. You can go up here and print this one page. Print. We'll see how goofy this is. And just put in the page number. It'll be page 22, the last one. And print to whatever printer that you choose to do. Alright, so. And then you can use this for anything. Remember, there's your hole, your angular value, your bolt radius, your relative x, your absolute x. And this particular problem, it's at 0, so it doesn't matter. You don't even need to fill this out. Unless we change the center of the circle, then you would have to put in your absolute values, right? So I think that's good enough for this particular bolt circle. Go back through and watch this section of the video and see what happens. Now, I talked to you about radians versus minutes of angle. We did that, remember? Remember we did that? I said that we were going to do that. So let's erase all of this trash off of here. Do I still have that in the snipping tool? Oh, I do. I'm just going to copy this. Here. It'll be easier to clean this up like this. And then paste the circle back in. All right, so now we said that the circle is 360 degrees, yeah? It's 360 degrees. What's going on? Or it's 2 pi radians, all right? So that means the value of 2 pi equals, what is going on? Oh, I've lost the internet, it's acting stupid. Here, close. Close that window. Not connected, that's fine. Exit Skype. There we go. All right, let's go back over here. Maybe it'll start behaving. That 2 pi equals 360 degrees. All right, so a circle can be measured in radians or degrees. Radians are degrees. So we want to talk about milrads or minutes of angle. And all that means is if you're ever into long range shooting, you might see a reticle that looks like this. Where the dots would be milrad dots. And each one of these has a distance of each one of these milrad dots, depending on your scope manufacturer, are generally a milrad. And what's a milrad? Well, it's a milrad is 1/1000th of a radian. Mil is 1,000th, so milrad. So in other words, it's 1/1000th of 2 pi, or it's 360 degrees. Okay. All right. So you have pi in here someplace. Function. Where's pi at? I can't believe we don't have a pi key on here. There's got to be a pi key someplace. There it is. So pi times 2. All right, so it's 6.283. Okay. So we say 6.283 equals 360 degrees. All right. So let's do a minute of angle first. Let's do a minute of angle first. So if we have our triangle, our right triangle, and we're going to say that this angle is 1 MOA. 1 minute of angle. And let's say this is 100 yards. And let's say it's 100 yards. So 100 yards is 300 feet, right? 100 yards is 300 feet times 12 inches, and it's 3,600 inches. So we're going to say it's 3,600 inches. 3,600 inches. We want to know what the opposite side is. So at 100 yards, what is 1 MOA worth? Well, we have angle, we have adjacent, or horizontal, and we have vertical. So we're going to use the tangent function, right? We're going to use tangent. So, and since we've got the opposite and the adjacent and the angle, we're going to use the tangent function. So we got to come back over to our formula sheet to make sure that we pick up the right formula. Go to trig expanded, and what do we want? We're using tangent. We want to know what the opposite is, so it's going to be the tangent of the angle times the adjacent side. The tangent of the angle times the adjacent side. Okay. So in this case, the opposite equals tan times the tan of the angle times the adjacent. That's tan. Okay. All right. So what is 1 MOA? What is that? What size is that angle? Well, we said that there are 60 minutes in 1 degree, didn't we? So we said that there was 60 minutes equals 1 degree. 1 degree. 1.1 degree, right? Okay. 60 minutes equals 1 degree. So what's 1 minute in degrees? 1 minute equals what? How many degrees? Well, when you come over here and divide 1 by 60, wouldn't you do that? Or if you're using this calculator, you could just say 60, that's the x. And what is 1 over 60? Wow, look at that number. It's 0.01666666, way out to silly land. Okay. So 1 MOA is, what did we say it was? 0.016. And it repeats out, and that calculation ended up at 7 at some point, right? Okay. Now, so that's our angle. So we're going to take the tangent of this angle, and we're going to multiply it times 3,600, right? So if we want the opposite side, equals the tan of this angle here times 3,600. All right, so let's go back to our calculator. We already have that angle in there, do we not? So let's go back to the calculator. So this is our angle. Let's go take the tangent of it. Wow, that's 2.9. No, it's not. Look over here. Look over here. You see this little E? You see this E right here? You see this E? The -4th? That means that we're going to move this decimal place over 4 times. So let's go back to our scratch pad. So we're going to call that 2.90888. We said that was 2.9. 2.90888. Right? Okay. Now what we said? 0.9088. We'll give it another 8. We'll give it one more 8. To the -4th place. -4. Right? E to the -4th. E to the -4th. That means we got to come over here. We got to move this decimal place 4 times. So let's change colors. So we're going to go 1, 2, 3. Oh God, we got to do another 4, right? Put another 0 there. So we moved it 1 place, 2 places. So we moved it 1 place to here, 2 places to there, 3 places to there, and 4 places to there. Right? So we moved it. We moved this 1, 2, 3, 4. We got to put zeros in front of all this. So there's our dot. There's our decimal place. So now that's 0 point. So it's 0.0002 90888 all the way out, and we would get rid of that. All right, so that's our angle. Okay, that's our angle. So now that we got this monstrosity in the calculator, we're just going to multiply that times 3,600 inches. And our opposite side now is 1.04719. Now we'll go to 3 decimal places. If you want to go to 4, then we'll round the 9. If you want to go to 4, we would round the 9. If you want to go 4, we would round the 9 up. So that would be 1.0472, 1.0472, 1.0472. Okay. All right. So it's 1.0472 inches. So by doing this, the opposite side is 1. Is 1.0472 inches. 1 minute of angle at 100 yards, 3,600 inches, is 1.0472 inches. Now, your granddad or somebody probably told you you can average a minute of angle to be about 1 inch per 100. Well, that's fine if you're only shooting at 100 yards. But what if you're shooting at 1,000 yards? What if you're shooting at 1,000? And then 1 minute of angle is 10.5 inches, not just 10 inches. And that could mean the difference between an X and a 10 in 1,000-yard prone. All right. So again, it depends on your degree of precision you're looking for. I want as much as I can. So a true minute of angle equals 1.0472 inches at 100 yards. Now, what about a mil rad? What about a mil rad? What about a mil rad? Okay, we're back. Took a sharp pause. All right, what about the radians, mil rads? Well, if 2 pi radians equals 360 degrees, if 2 pi radians equals 360 degrees, then 1 radian, come over here, if 2 pi equals 360, and those are radians, then that means 1 radian looking at the wrong screen. 1 radian equals 360 degrees divided by 2 pi. Okay. So 1 radian is going to equal, if we do the math right, excuse me, 1 radian is going to equal 5.295777951 77951 degrees. Now we could round this to, let's say, 4 decimal places. 1, 2, 3, 4, go to the 5th. That's greater than 5. So we could say that this is going to be an 8 instead of a 7. So we could say that it's 57.2958 degrees, all right, is 1 radian. Now a mil rad, like in a military sniper scope, and I've got both mil rad scopes and MOA scopes, and they all have their place. All right, so 1 radian. So if we do a thousandth, and that's what a mil rad is, it's 1 rad divided by 1,000. 1 radian divided by 1,000. Then now the degree becomes put a 0 in front of the dot. If I haven't told you to do that before, just do that. Is 0.572958 2958 degrees. Now we're going to go through the same exercise that we did up here. We've got a triangle. I don't know about y'all, but I sure get tired of these spam calls. They want to sell me everything from, they want to buy my house or whatever. The Medicare. All right, so we're looking for the opposite. You already know the magic formula for it. This is 3,600 inches, right? Because it's 100 yards. All right. right, we're still going to use tangent. Where are you going to use tangent? Of the angle times the adjacent side, which is 3,600 inches. This is the adjacent side, right? This is the adjacent side. All right, and this equals opposite. All right, so go to our calculator and let's do that. 0.057298. So let's go to our calculator. All right, let's clear this out. We're going to go 360 degrees divided by 2 divided by pi, wherever pi's at, divided by pi. All right, and we get 57.2957795, da 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 da. Now this is going to be a thousandths, right? A mil. So we're going to have to divide that number by 1,000. Move the decimal place over 3 times, right? And so that's our degree of 0.057295. We round it to 8, but let's leave it in the calculator and see what happens. All right, so we want to take the tangent of that. That's our angle now. We want to take the tangent. We want to multiply that times 3,600 inches. And we end up with 3.6 inches. And if you round it to the 5th decimal place, if you round that number to 0.057298, you still get 3.6 and a bunch of zeros before you hit your 12. So we end up with the same number at 100 yards. So this is our opposite side in inches. This is our opposite side in inches. So the opposite side for 1 milrad, the angle is 1 milrad, or 1 mil. We know that the angle really is that in degrees. And the opposite side is 3.6 inches per every 100 yards. So at 1,000 yards, that's 36 inches. Now, if you're trying to hold a 2.5-inch circle at 1,000 yards for target shooting, what are you going to want? MOA or milrad? You're going to want an MOA. Now you can range with an MOA reticle and you can range with a milrad. Milrads are faster for snap shooting, and if you're just trying to range to hit a human target at distances, then that's fine. You're not doing target shooting. For hunting, I don't have a problem with either. I don't have a problem with a milrad scope. I've got several hunting rifles that have milrads on the scope. They're marked in radians, mil radians, and I've got plenty of target scopes that are marked in MOAs. Okay, MOA scope's going to have a lot of little marks in them. Okay, and I've got some that are milrads with the dots, and then there's a half a dash between the 2 dots for a half a milrad. You just want to make sure that your turrets that adjust your scope up and down, the turrets on the scope that adjust the scope for elevation and windage, are to the same measurement as your reticle. So if your reticle is in mils, milrads, then you're going to want your turrets in milrads. If your reticle is marked in MOAs, if this was an MOA and this was a rad, then you're going to want your turrets in minutes of angle, or some sub-minutes of angle, like an 1/8 minute of angle. All right, so windage and elevation. So that's the difference between your MILRAD and your MOA. So your MOA is roughly, what did we say that was? 1.0472 inches per 100, and 1 mil radian is 3.6 inches at 100. They're both fine. They both have their places. But like I said, if you're trying to hold a 2.5 inch circle, a 2.5 inch circle at 1,000 yards, all your bullets need to be in there, then you're going to want the more precise graded scope, which would be, in my opinion, an MOA. All right, that ends this video. We've added some extra stuff. You're not going to have any test on MILRADs, but you will have degrees, minutes, and seconds, and such as that.